As we continue to learn more about vectors, we know we can do things like add and scale, but of course the question comes, can we multiply? Well, in some sense, yes, because scaling is multiplying, where we take a vector, multiply by a number, and we make a longer vector or a shorter vector. But what about a vector times a vector? Wouldn't dot be interesting? Well, let's talk about a possible way to approach multiplying vectors together. Now, the sort of intuitive thing to do is if we were going to guess on how to multiply vectors, we'd say, well, when we add vectors, we add component-wise. So, add the first component, add the second component, add the third component, so forth and so on. Well, why not just multiply it entry-wise? So in other words, multiply the A and the D, the B and the E, the C and the F. That's so easy. It's so easy. It's obvious. It's easy to remember, easy to do. Life is good. Could there possibly be any downside? And there is a kind of a downside. It's useless. Now that's a very bold statement to say something is useless. So we want to take a second and say, what do we mean by saying it's useless? And in particular, what we mean is there's no geometric interpretation. You see, when we talk about calculus, we really think about what's happening in space. Now you might say, well, what do you mean there's no meaning? We have these numbers. How do you know that there's no meaning? Well, remember that space exists regardless of how we choose to describe it. And the way that we have these vectors are somewhat tied to our description of it. Remember that these entries here, the first, the third, and the second, represent the x, y, z. So it's tied to our way we're describing space. When we say something has a nice geometric interpretation, we say it doesn't matter how you describe space, it's independent of that description. So whenever we look for something that's useful, we have to keep that in the back of our mind. It can't depend on our coordinate system. Now let's take our two vectors and we'll mark them here. So here's two vectors, and we're going to look at two possible coordinate systems. So in the first coordinate system, we say, well, look, what if our vectors happen to line up with our coordinate system in a very nice way? Well, if they did, what you would have is you'd say, well, look, this is a case where in this direction, our first vector might look something like, well, some number comma 0, because it's going all in the x direction, none in the y, and the second one would be none in the x, all in the y, 0 and b, and we'd end up with 0, 0. In other words, we'd say, look, these two vectors, if we just multiply entry-wise, we get the 0 vector, which is a really special vector. It's that vector with no direction. But that's if we were in that particular coordinate system. We can choose any coordinate system we want to describe our space. Changing coordinate systems does not describe space. It changes the way we describe our space. And of course, that means that anything that's happening before that's in space still happens. So if we turn our coordinate system now, so that we have something like this, we say, well, what's happening? Well, if you look here, if we think of this as now being the x direction, this is being the y direction, well, we say now our vector, our first vector here, looks like we're moving some positive amount in the x direction, some negative amount in the y direction. So it looks like something like c comma d. And I'll put minus d just to emphasize sort of a negative y. And the other one, well, it's also moving a positive amount in the x direction, positive amount in the y direction. C comma positive d. So we end up with a c squared and a minus d squared. And what you notice here is that that's not 0. It's not the 0 vector. And so we see, aha, this particular product of vectors is dependent on description of space. And once we have that, we throw it away. We can't use it. We're looking for some nice product where when we combine vectors together, there's an interpretation that is independent of how we choose to describe our space. So at this point, you're probably thinking, boy, it's going to be tough to come up with something, but dot would be a mistake because we have one kind of simple variation that says, maybe we're trying to do the wrong thing. Maybe what we should be focusing on is, instead of trying to produce a new vector, maybe we should combine two vectors in a different way. And here, what we'll do is we'll say, let's sort of like embrace this, but instead of thinking of these as individual component entries, we'll just think of them as numbers. We'll add them up. And that is what is the dot product. So you still multiply, right? The first entries get multiplied, the second entries get multiplied, the third entries get multiplied. But now you add the results together. And so what we have is a vector dot vector, and the reason we call it a dot product is notation. Now this makes you highly suspicious, saying, is there another product? Well, we've already mentioned one, the scalar product. So now we have a scalar product, number times vector. We have a dot product, which is vector times vector. We'll do another one on another day. But for now, the dot product. So dot product notation is the dot. So when you see a dot being used with vectors, that means you need to have a vector dot a vector. Be careful with your notation. What's the result? A number. And the nice thing about the dot product, works in any dimension you want. So if I take A, B, C, dot, D, E, F, multiply the first entries, AD, plus the second entries, BE, plus the third entry, CF. And if I would do it in 2 dimensions, AD plus BE. And I could do it in 7 dimensions, or 15 dimensions, or 100 dimensions. I can do it in any number of dimensions I want. It's actually a very simple product to compute. Now, we haven't justified yet that it's a good product. So we're going to work on that. So we're building up to the goal of saying, is this something which is useful? And I'm going ahead and just spoil it right now. The answer is yes. This product is amazing. It doesn't depend on what our description of space is. It has a nice, always nice geometric consistent meaning. Wow, that's going to be cool. Okay, so let's get there. Well, one of the things we can think about are, what are some nice properties? So let's take a look at them, and I think none of them should surprise us. So for instance, it doesn't matter the order we take a dot product. U dot V is the same as V dot U. And you're probably thinking, well, that's always the case. Is it? Foreshadowing of things to come. Okay, so but why is that true? Well, it's true because multiplication order doesn't matter. If I swap the vectors on this side, it's sort of saying, well, it's dA and AB and EB. Oh, look, they say the same thing. I can have a constant here. I can pull the constant out. Well, that's true because I'll have a constant in each entry. I just pull it out. No surprises. I can distribute. So if I have U dot V plus W, it's U dot V plus U dot W. And again, it's easy to check. You just say, let me run through the computation. And I see that what's happening is I can use the properties of multiplication, and whatever properties of multiplication are, I can transfer them to properties of dot products. Because ultimately, in the end, I'm really using multiplication entry-wise. And it's just the fact that I'm adding things together. If I take the 0 vector dot any vector, I get 0. Well, that's easy to believe, because the 0 vector, if we think about it entry-wise, it's 0, 0, 0. So if you multiply everything by 0, you get 0. Now, here's where we start heading towards geometry. If I take a vector and I dot it with itself, so now U dot U, it has a meaning, and it's the magnitude of U squared. Now, why is that? Well, if you just think about what U dot U is, see, if I look at the vector U, one way to think of the vector U is it's really change in X, change in Y, and change in Z. Where X, Y, Z, okay, that's my coordinate system, that's fine. It can be any coordinate system I want. When I take U dot U, what's the result? Well, it's you multiply each entry by itself. So the result is you square each entry. So it's the change in X squared, the change in Y squared, and the change in Z squared, all being added together. But we know about distance, and we say the distance between 2 points is you take the change in the X squared plus the change in the Y squared plus the change in the Z squared. It doesn't matter how your coordinate system is built. That's always still the case. And so there we go. That's really just the distance between the start and the end of the vector, and also by the definition that we've seen for magnitude of vectors, it's the magnitude of the vector squared. So now we have a connection, a nice geometrical connection. Now, it's tenuous right now, but we're going to go one step further. Our goal is to say, all right, we can do u dot u. What about u dot v? Good. Great question. So here we go. And we're going to start with a little reminder from trig. It's called the law of cosines. Now, if you don't remember the law of cosines, think of it as Pythagorean theorem for triangles which aren't right triangles. Now, what does Pythagorean theorem say? It says, well, a squared plus b squared equals c squared. The law of cosines says, well, it's almost always the case that a squared plus b squared equals c squared for any triangle, but you kind of have to do a correction. So it depends on what the angle here is. So if I think of this as being sort of the opposite angle to the hypotenuse, then there's this extra piece, 2ab cosine theta. Now notice, when theta is a right angle, cosine is 0. So that's where you get a squared plus b squared equals c squared. So it really is a generalization of the Pythagorean theorem. And Pythagorean theorem connects to distance. Well, that's a good clue that there might be a nice connection here with dot product. So we're going to use the law of cosines and a little bit of dot product, and let's see what we have. So let's suppose I have two vectors. So I've marked two vectors here, and I've put them together. And when I say I've put them together, remember, vectors aren't tied to location. So I can take my vector and I can move it wherever I need it to be. You know, just be careful because the ends can be sharp. But okay, so we're going to move our vector so that the tails or the start of the vectors are in the same place. So I have a vector u and a vector v. And now we say, well, that's two sides of a triangle. We can find our missing side. The way we do that is we think about, all right, let's think about this last vector here. Now, my claim is that it's u minus v. Well, let's reason why that would have to be the case. Let's think about starting at this point and ending there. Well, one way to start and end is to just go right along u. Okay, so that's u. The other way to do it is to go along v and this other vector. So what we have is that u has to equal v plus whatever that is. All right, so u equals v plus something. Well, now subtract v. We can do that. The way we can subtract v is really add negative v to both sides. And the v and the minus v cancel out. We get u plus negative v, or u minus v, is our missing vector. So now, what's our goal? What's the length of this side? And in particular, we're going to say, what's the magnitude of u minus v? Remember, that's the length squared. Two ways. So, what's our first way? Well, u minus v is a vector. And we've just seen that when we take the dot product of a vector with itself, it produces the magnitude of that vector squared. Aha. So, we're going to take u minus v dot u minus v. Now, you might say, ooh, that kind of feels like foiling, because we're going to FOIL. You see, the ability to distribute through, that distribution property, is what allows foiling to happen. So we'd have u dot u, then we'd have a minus u dot v and a minus v dot u. But u dot v and v dot u are the same thing. So we could really say it's two copies of u dot v. And then on the end, it'd be a v dot v. And now we say, well, okay, so u dot u, that's just the magnitude of u squared, and v dot v is the magnitude of v squared. And then we have this leftover piece, which is u dot v, which is what we're trying to understand. Okay, so now we said we found the length of sort of this third side squared by using dot product. We're going to repeat it now and say, let's come back and use law of cosines. So if we think about law of cosines, we say, all right, look at our picture. Our lengths of our sides are just the magnitude of these vectors. And so what we can say is that the magnitude of u minus v squared is the magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u magnitude of v cosine theta. And what we're doing is we're just thinking, well, look, here's A, there's B, and there's C. And applying the law of cosines. Just straight up law of cosines, nothing else. Now, here's our great moment, to be followed by even more moments. So, what's our great moment? Well, we're computing a value. It shouldn't matter how we compute it. The value should always be the same. Now, what does that mean? Well, that means that if you look on the very end, these pieces here, that's where they differ. So these parts have to also be the same, because you can see that the magnitude of u squares, magnitude of v squareds match. So these have to match, which tells us u dot v has to equal magnitude of u, magnitude of v, cosine theta. So this is kind of cool. In fact, it's really amazing. So what does it say? It tells us, hey, this has a geometrical meaning because I can compute dot product without ever having to do anything involving multiplying the components together. What do? What I do is I come along, and if I have a vector u and a vector v, I say, well, look, if here's u and here's v, and well, maybe not quite like that because that's too close to that picture. Here's u and here's v. What I do is I make sure the tails are together. In other words, they start from the same point, and then I say, well, look, there's an angle here. So then the dot product is I measure the length of u, I measure the length of v, I multiply it by the cosine of this angle. All three of these things, the length of the first vector, the length of the second vector, the angle between the vectors when I put their tails together, all of those are geometrical things that can be measured. They're geometry. And then the dot product says you multiply the magnitude of u, that length, magnitude of v, that length, cosine of the angle between them, and that's the dot product. So I have a purely geometrical interpretation. So that says the dot product is going to be awesome. Woo! Dot product is in the house. This is going to be good. Now, one of our immediate consequences is it says, well, you can actually sort of now reverse engineer and find an angle between vectors. See, I can take this and divide and say that cosine of theta is u dot v, and divide that by magnitude of u, magnitude of v. And now I have an expression for cosine theta. And of course, if I have cosine theta, I can take the arc cosine. So we can find angle between vectors using this approach. So this is a nice kind of application of dot products, as it helps us find angles between vectors. Now, there's one very important angle that shows up frequently, and that is right angles, because after all, it is the right kind of angle. And we know something about a cosine of a right angle. Cosine of a right angle is 0. So when I look at the dot product of u and v, if they have a right angle here, the dot product is going to be 0. So we have a sort of a definition. We say that two vectors are orthogonal, or we sometimes say perpendicular, if and only if their dot product is 0. All right, good. Now, by the way, you'll sometimes see this written as u is, they have this little symbol that looks like that. And that, when you see this symbol, you should think of this as being perpendicular. U perpendicular to v. So what does this mean? Well, it means that we have a way to test if two things are perpendicular. And perpendicular is kind of a nice idea in geometry. When you think of the geometry here, geometrical intuition, one of the things that often happens, for instance, is if we're trying to have things be as close as possible, oftentimes we say, oh, well, there's going to be a right angle formed. because that is going to somehow be the closest. If it's not a right angle, we can perturb to get up to a right angle. That would shorten the distance. So having things be perpendicular is a very common thing that happens when we're thinking about problems from a geometrical perspective. So dot products are going to be useful in that sense. Now you might ask the question, what about the zero vector? Well, that gets to an interesting question, because we say the zero vector has no direction, but by this convention, if we take u dot 0, it's always 0, because we've mentioned that already. So we say, well, the zero vector is perpendicular to everything. Or perhaps we can say the perpendicular is orthogonal. There's a little bit of a gray area with the zero vector, but generally speaking, don't worry too much. Just say, look, the zero vector, we're always going to say is orthogonal to every vector. All right. So now we have this beautiful idea. We can have this nice geometrical interpretation. We can do one more thing with this. So we're going to talk about projection. So here's sort of the notion of projection. So imagine that I had a very bright lamp. So here's my lamp, and it was shining a light down from above. And what I see is I see that there's a vector, and there's two vectors here. So I want to be clear here. You can't quite tell the color coding here, but I'm going to help you by color coding along here. So let's make this u. So here's the vector u. And now there's another vector v. And here's the vector v. And finally, there's a question. What is the amount of u that points parallel to v? Now you might want to say, what? What are you talking about? Well, let's think about sort of an analogy of where we're going. So you might imagine that you're in the winter and you have driving through the snow. Your car gets stuck. And here I've drawn a car. Now you might not be able to tell it's a car, but now you'll see that you say, aha, yes, I totally see now. That's a car. And if you live in a very friendly place, and I hope you do, you'll see that all of a sudden people start showing up and they start pushing your car to help you get out. Now, you might have a lot of people pushing on the car, and you start noticing something. If you have a lot of people, the people who are in the back pushing in the car, they are sort of more effective. While the people who are pushing sort of from an offset angle are less effective. You see, what's happening is that when a person is pushing from an angle, part of their force is being directed in the correct direction, and part of it is being pushing the car perpendicular to where it wants to go. So in some sense, we have to ask, well, how much is this person helping? Well, what we can do is we can ask the real question, how much of what the person is pushing is helping us go in the same direction as the direction that we want the car to go. So that's what projection is. It's saying, well, let's understand, if I have a vector that says this is the direction of this current vector and its magnitude, how much of that vector is in another given direction? That's our goal for projection. Now, there is one small thing to be careful of, and I do want to be a little bit cautious here. Notice we say the word parallel to v. So we don't necessarily have that u points in the same direction as v. And you might say, how? How? And the answer is seen in the following. You could say, well, if you have v pointing in this direction, and then u comes off at a very particular angle, say this way, then what will happen is that when you do the projection down, you'll have that the projection points not in the same direction as v, but actually in the opposite direction of v. But it's still parallel to v. Okay, so now we have sort of our goal. We're trying to understand projection. How much of one vector points in the direction of another vector? So we have to start thinking, how do we figure out how to answer this question? Well, whenever we have a question about vectors, we always say, well, any question about a vector boils down to asking ourselves two sub-questions. What is the magnitude of the vector? What is the direction of the vector? And if we understand the two properties, a direction and a magnitude, then we understand the vector, because that's the two things that make up a vector. So we've now turned our problem of saying, well, what's the projection, into saying, well, what can we say about the direction and the magnitude of our projection? So let's get into that. We'll start with the direction, because that's actually probably the more intuitive. Remember, we want to say it's parallel to the direction of the vector we're going onto. So if we talk about the projection, now here's our notation, the projection of u onto v. Well, that says if I'm going onto v, it needs to be parallel to v. So the way that we find the direction of v is we do 1 over the magnitude of v times v. Why? Well, remember how we think about direction. The way we think about direction is take a vector, scale it so it's a unit vector. Anytime we're really after understanding a direction, we say, let's turn it into a unit vector. So unit vectors are our way to understand direction. So here's our direction. Now, the magnitude. Okay, so for this, we have to think of the picture. So let's be a little bit, we'll go through and draw our picture here. So we have our v, and here's our u. And now we have an angle here. We'll mark it as theta. All right, so if we're after our projection, well, what happens is we say the projection would be if we came straight down, because we think of the light coming from above, straight down, so it shines the light straight down, and then this part right here, that's our projection. So we're really after understanding that length. So we look at this triangle and say, all right, in this triangle, what do we know? We know the angle between the vectors, and we know the hypotenuse. The hypotenuse is this vector u. We don't know this side. Now, we know the direction of this side, but we don't know the length of this side. In fact, if we think about it, the length of this side is really what we're after. That's what's going to give us the length of our projection. So we look at our picture and say, all right, what do we have? Well, we want to know the adjacent side. We know the hypotenuse. The hypotenuse, in terms of length, has magnitude of u. So the length, which I'll write that as a question mark, divided by, so that's the length of the adjacent side, what we're after, divided by the magnitude of u. So adjacent or hypotenuse is the cosine of theta. Now you multiply it through, and now we have, magnitude of u cosine theta. That's the length of our projection. Well, almost. I have told a tiny, tiny little white lie, and so I'm going to just correct myself right now and just say, you notice how we've marked not just direction, but we've had these little quote marks here, where we've had direction and magnitude. And here's the little white lie and why it works out to be fine. If we are in the situation where the angle is acute, in other words, it's less than 90 degrees, then it's true that the direction and the magnitude are exactly what we've talked about. If we're in this case over here, where the angle is above 90 degrees, so we would call that obtuse, it's actually not quite right. What happens is that the direction is opposite, which introduces a negative sign, and then what happens to the magnitude is that the cosine is negative, which of course is another negative sign, because magnitude should never be negative. But the good news about multiplication is two wrongs make it right. Negative times negative, it all works out. Beautiful. And so we have the following. The projection is our magnitude of u cosine theta times 1 over the magnitude of v times v. All right, there we go. Our length times direction. And we can have it all work out. It all fixes itself in the end. Now, we want to make that a little bit simpler. So, what can we do? Well, we can say the following. Look, let's just put things together. Magnitude of u cosine theta over magnitude of v. So that's a number times a vector. But we look at that and say, that's kind of messy because we'd have to know what cosine of theta is. And then we start it for a little bit and say, this looks a lot like a dot product. And indeed, it is a dot product if we had one more thing. Well, the theta is our angle between our two vectors. So if I want to turn this into a dot product, I just have to put the magnitude of the other vector. So if we go from there to there, we added a magnitude of v in both top and bottom. And we say, perfect. Look at the top. It's u dot v. It's the magnitude of u, magnitude of v cosine theta. Look at the bottom, magnitude of v squared. That's v dot v. So what we end up with is our projection is u dot v over v dot v, and then times the vector v. Now, in some sense, you're probably thinking, oh, look, this makes perfect sense, right? Because you say, well, I canceled the v's, the v, and the v, the v, and the v, and I'm left with u. But of course, that's not what's happening here. So be careful. That's not how cancellation works. You can't take a number like 16 divided by 64 and say, look, all you have to do is you just cancel the 6's, right? And you get 1/4. That would never work. Wait, what? Oh, that is work. Oh, okay. Well, that's just a coincidence. In practice, it never works. I'm sure if we tried it again, okay, like 19 over 95, right? Cancel the 9's, right? And what would that tell you? It would be 1/5. And the answer is, oh, wait, it's actually 1/5. Okay, never mind. Those are just two kind of crazy examples. So, but it's not the case that you are canceling the v's out and you end up with u. But it's not a bad way to sort of say, oh, it kind of intuitively makes sense. So there we go. There's our nice projection formula. Now, one last idea. And this is going to be an important idea as we start understanding vectors. Because we said, look, we can ask the question, when we talked about pushing the car, we said, well, in one direction, this person pushing from a diagonal, part of it was useful, part of it was wasted. Essentially, there's a part where they were pushing the car sideways and not forward. So you might want to say, well, can we take a vector and sort of break into the parts, the useful part and the wasted part? Another way to think about it is the useful part is parallel to the direction we want. The wasted part was perpendicular. And the answer is yes. And in fact, it's a very easy process. And the picture tells us what to do. So we start with the following. If we have our vector v, so here's our vector v, and we have another vector u, and we'll put it here. Here's our vector u. Then what we do is we really think of our vector u as being two parts. So one part is this part right here. And this part is the projection of u onto v. So that's the part of u that's pointing in the direction of v. And then the other part is this piece. Now, how do you find that part? Well, what you do is you say, if I know the useful part, I can subtract it from u, and that's the sort of perpendicular part. So if I want to break it down to have something which is parallel to v and something perpendicular to v, well, projection gives the parallel part. Then if I subtract the projection from the vector, that gives the perpendicular part. And you can see it works out, because what happens? These projection cancels out. And you can also check, it's actually a pretty straightforward check, if you were to take the dot product of these two vectors together, what would happen? Well, the answer is it should be 0, right? Right? Let's actually check that. So our claim here we'll do it on the side, is if we take the projection of the vector u onto the vector v, and we compare it to the vector u minus the projection of the vector u onto v, these two should be perpendicular. Now, how do we know if two things are perpendicular? Well, we've actually talked about this today. Two things are perpendicular, we have a fancy word, if they're orthogonal. They're orthogonal if their dot product is 0. So what we need to check is we say, let's take these two vectors and we're going to compute their dot product. So we start with our projection. We're going to write what it is. It's this constant u dot v, v dot v, times v. I'm going to suppress the arrows just to make it simpler in our computation. Okay, so that's what we're going to dot, and then we're going to dot it with u minus u dot v over v dot v times v. So, well, the nice thing is we can, of course, distribute through. And what do we have? Well, we have from the first term this constant u dot v over v dot v, and then we have v dot u. So that's the first piece. Minus, from the second piece, u dot v over v dot v, and there's a u dot v over v dot v, because it's this constant, that constant, and v dot v. And now we say, aha, look, almost as if it was meant to happen, because it was meant to happen. The v dot v's cancel there. We have a u dot v and a u dot v. These are the same. U dot v and v dot u are the same. So u dot v squared over v dot v, u dot v squared over v dot v. And so indeed it is 0, which means, aha, we were correct. Things were indeed orthogonal. So that's how you can take any vector you want, and really any pair of vectors, and say, how much of this vector points in the direction of that vector? How much of this vector is perpendicular to the other vector? And we're good. I will say that there's kind of a fun application that you can do with dot products. In some sense, when we're thinking about dot products, it helps us measure the angles between vectors. So generally speaking, when we have a dot product where the angle says the angle is very close, the vectors are pointing in a very similar direction. Where when the angle is fairly large, it means the vectors are pointing in a very opposite direction. So how can we use that? Well, one thing you can do is you can have people fill out personality surveys. And then you can have it somehow be sort of a measurement of preferences. And now what you have is you have a set of data. Well, you can turn that into a vector. And so that vector represents certain traits and interests and personalities. And now you say, well, people should be compatible if the vectors have a very small angle, which says something about the dot product, and they're very incompatible if the vectors are very large. So somehow the dot product is a measurement of closeness. How much do things point in the same direction? And, well, I don't recommend using math to find romance, but of course, it doesn't hurt, right? After all, mathematicians are lovers at heart. We love solving problems. All right. Well, thanks for coming, and let's go do some practice.